Okay, 7.5, solving linear trigonometric equations. We learned in lesson 7.4 how to prove trigonometric equation is an identity. That's when all the x values are true for the given equation. So for sine squared x plus cos squared x, any value of x will result in the value of 1. For other equations, that's not quite the case. So for this equation, 2 sine x minus 1 equals 0. This is not an identity because not all values of x would result in a value of 0 here if we subbed in different values of x. But however, just like any algebraic equation, we can still solve this for different values of x. Okay, so that's what we're going to learn about today. So the first equation is true for all values of x in the given domain, so it's an identity. The second equation is true for only some values of x, so it's not an identity. So how can we solve a trigonometric equation that is not an identity? Selecting a strategy to determine the solutions for a linear trigonometric equation. So you're given the equation 2 sine x plus 1 is equal to 0. And here's an important part. Because we're dealing with trigonometric functions here, and they all go on for infinity, or at least cosine and sine, they continue on for infinity. You'll see always a range or a domain that they give for you to solve within. All right, that's important because otherwise there's going to be kind of an infinite number of solutions. So we want to know what values of x is this equation true between 0 and 2 pi. So determine all the solutions in the specified interval. So the first steps are the same. We use the opposite operations in order to isolate for x. So we move the 1 to the other side, we divide by 2, and we find out that sine x equals negative a half. Okay, this is a particularly easy question because we know the value of sine x is equal to a half. We know what that acute angle is because it's a special angle. It's in our special triangles, right? We know the value of x when sine x is a half. Okay, does anybody remember that?
Root 2 over 2.
What's the angle? Root 2 over 2? Yeah. Okay, no, that's when x is not a half. This is, in this case, root 1 over 2, right? What angle of that?
45.
No.
30. Oh, shit, sorry, my bad. My bad.
Right, it's angle pi over 6 or 30 degrees. If we're dealing with radians, it's pi over 6. If we're dealing in degrees, it's 30 degrees. Any questions about that so far? Okay, so there's one issue with that though because of this negative sign. Okay, so that's pretty much the big trick today is how to deal with that negative sign. So if we look at that on a graph, here's our y equals sine x graph. We can just go down to the value of negative a half, which is here, and we see where those two x values are. So remember, this is our y value, negative a half. So we go down to y, negative a half, and we put those two dots there so we can see that these are actually our x values right here and here. These are our x values, our value of x when y is equal to negative a half. Okay? So another way to think of it is if we look at our 4 quadrants. Okay? So we know that this acute angle when sine x is a half, we just said that this is pi over 6, right? That's the acute angle when you're solving for it for positive. Because it's negative, because sine is negative, we have to realize that it has to be in either the 3rd or 4th quadrant. Why? Because it's negative. Those are the only quadrants that sine is negative in. Okay? So we need then to solve for this angle and this angle. Those will be our answers. Okay? The way we get those angles is if we know the value of the acute angle, which is pi over 6, we can add pi over 6 to pi, and we'll get this angle, right? From here to here. So we have pi plus pi over 6. All right? So now if we look down over here at this value, we can also see that it's the same, right? This x value is 7 pi over 6, which is right here. The other one now, we're going to take 2 pi and minus pi over 6, right? Because we're looking for this terminal arm now. So we take 2 pi and minus pi over 6. Any questions about that? So the key then is just really to understand your cast rules. When are the sine, cosine, or tangents value positive or negative? And then to find the acute angle, which is always positive, you find the acute angle first. In this case, it was 30 degrees. And then take that related acute angle and apply it to the different quadrants. That's what we're doing. Okay. So here's that process that they took, the same as I showed you on the other side. Pi plus pi over 6 is 7 pi over 6. So there's that angle in blue. And then here's the angle in green. They took 2 pi minus pi over 6 to get this angle. How else could have we got this angle? Instead of 2 pi over 6, we could have done what? 2 pi minus pi over 6, we could have done... Anybody?
270 plus pi over 3.
Right, we could have went from here, yeah. We could have went 270 plus 60 degrees pi over 3, okay? But pi over 2 pi minus 30 is a lot easier, okay? It's best to work from the x-axis always, okay, as opposed to anything on the y-axis. Next is we graph to just prove those, and they find on the graphing calculator that the values are the same, which are right here. Okay? Let's see some reflecting questions. How was solving the equation 2 sine x plus 1 equals 0 like solving the equation 2x plus 1 is equal? How was it different? How was it the same? Sorry?
You have to isolate for x.
Right, isolate to x. So we use those opposite operations, right? Which were essentially identical. You move the 1 to the other side and then you divide it by 2. How was it different? Well, at the end, what did we have to do? There was some other stuff we had to do, right? So we could just say that there was more steps required to find final answer.
So one, there's 2 different values.
Sorry, David?
For one, there's like 2 different values for the sine x.
Yeah, exactly. You're right.
Good job.
So instead of just being one value, you're right. There's 2 different values. Why? Because the trigonometric ratios are repeating themselves, right? Once sine x was isolated in example 1, how was the sign of the trigonometric ratio used to determine the quadrants in which the solutions were located? Yeah, Alex?
Since it's negative, it can't be in the quadrant 1 or 2 because sine is positive in those quadrants.
Right. So it was negative, so sine had to be in the 3rd or 4th quadrant. And we have to remember that pattern. The interval in example 1 was between 0 and 2 pi. If the interval had been xer, how many solutions would the equation have had? Yeah. Infinite, right? If it would have just kept passing by the value of negative a half. So there would have been infinite number of solutions. Okay, using an algebraic strategy to determine the approximate solutions for a linear trigonometric equation. So basically the same thing. This time we're working in degrees, no difference. Some of you might even prefer it. So between 0 and 360. Correct to 1 decimal. So the first thing we do is our reverse operation. So we're multiplying by 3, so we divide both sides by 3. Adding 1, we subtract 1 from the other side. So we end up with this, which I think all of you will get to no problem. The next part is now to understand, first of all, what is the acute angle? What is the positive acute angle? So in other words, what is tan negative 1 of 1/3? That's the first step. You wouldn't put negative 1/3. You just want to get the positive acute angle of 1/3. Okay, which is 18.43. And you're going to do that on your calculator. Okay, it's not a special triangle. It's in degrees, remember, so you have to do that on your calculator. So once we have that acute angle, that's this angle right here. This is 18.4. Now we look at the sine and determine what quadrants are these in. Because it's negative, there's two quadrants that it could possibly be in. It has to be the second quadrant or the fourth quadrant because we're dealing with tan. Okay? So I take that acute angle that I drew, the 18, and I draw it in both the other quadrants that it has to be in, which are negative. And then I try to find those angles, this one and all the way around. Okay? The way we do that is we take 180 now, because we're working in degrees, 180, and we minus that acute angle, and we take 360 and minus that acute angle. Okay, so it's pretty straightforward. So we should have 180 minus 18 and 360 minus 18. So that's where we are down here. 180 minus 18.4 and 360 minus 18.4. So there is our two values. Okay, and we say about because we rounded. We rounded that 18.43 to 18.4. Any questions with that one? So it's pretty simple stuff, right? The only tricky part is to just realize what quadrant the different trigonometric functions are positive and negative. Example 3. Okay, word problem. Today the high tide in Matthews Cove, New Brunswick is at midnight. The water level at high tide is 7.5. So we're going to start our graph off and draw at 0 or midnight a height of 7.5. That's our water height. The depth, d meters, of the water in the cove at time t in hours is modeled by this equation. Jenny is planning a day trip to the cove tomorrow, but the water needs to be 2 meters deep for her to maneuver her sailboat safely. Very familiar to us, similar to the other questions we've received. How can Jenny determine the times when it will be safe for her to sail into Matthews Cove? So they need to be at least 2 meters deep. So on our graph, we can look at 2 meters and we can see those times right away. So that's what we did in the last section. Now we're going to find exact values. Okay, so we're going to create an algebraic equation with this model and find out the exact values as opposed to just drawing a sketch and seeing them on the graph. Draw a rough sketch of the depth of the function for at least the next 24 hours, assuming that t equals 0 is the high tide at midnight. So here's our graph. We know a bunch of things from this equation, right? We know that 4 is the equation of the axis right there. Okay, that comes from here. We know that the amplitude is 3.5, so we go up to 7.5 and we go down to 1.5. And then we also know the period by taking the value here and dividing 2 pi divided by this value because of our formula right here. Okay, so our period becomes 12. All right, all of that is review. Okay, so we have this graph. The next thing we want to do is what we're learning in this section 7.5 is we want to set all this whole equation equal to 0. Why? Because we know that at the depth of 2 meters it's safe to leave, so we're going to set the depth, which is dt here, to 2. Okay, and then we're going to solve it algebraically. So we combine like terms, moving over the numbers to the other side, divide by 3.5. We have this term now. Cos pi over 6 times t is equal to negative 2 over 3.5. So this is a tricky one here because we need to take the cos negative 1 of negative 2 over 3.5. This is going to give us not the value of t, but the value of pi over 6t is going to be equal to this value. So what's the cos negative 1? 0.96. Okay, and of course we're dealing in radians, so this value does make sense. 0.96, close, somewhere around 60 degrees. Or 60. Actually, sorry, we're dealing with time units, so it's not an angle. So now we can solve for t. So now we have to multiply both sides by 6. So we have pi t is equal to 6 times 0.96. Actually, hold on. Before we do that, let's leave it at 0.96 for now. Let's leave it pi over 6t at 0.96. The reason I say that because we need to determine first actually what quadrants we're dealing with, where we're working. Because it's cosine, we know we're going to work in either, sorry, because it's negative and it's cosine. So see we have this negative sign here. We know we're going to be working in the second and third quadrants. So we want to find this value first actually before we go ahead and multiply. So the first thing we do is we find the angle, which is 0.96. We have that. So there's our acute angle of 0.96. We want to find those related angles in the second and third quadrants. So we take pi minus 0.96 and we take pi and we add 0.96. So that's going to give us 2.18 and 4.1. So that's right here, here and here. Any questions about that? Why we did that? The same process. The only difference is that we had pi over 6 in front of the value of t. So we're finding those angles before we solve for t. Once we have those values, 4.2 and 2.8, then we can go ahead and solve for t. It's quite straightforward. We multiply both sides by 6 and divide by pi. So the 4.6 becomes 16.16. And the 4.1 becomes 19.83. Finally the last step, sorry I missed that, it's 7.83 and 4.16. And then we can add, you can generate more solutions by adding 12 to the period. So if you're given a range, in this case we were given the range 24 hours. Okay, so this is the last important step. You need to be within that range. So we solved for, here were our values, 4.16 and 7.83. You need to add the value of 12 or the period to find the additional values that are all within that domain. Okay, so here's our 24-hour period. We needed to find all four of these. When we solved, we only found these two, 4.16 and 7.83. You need to take the value of 12 and add that to each one of those to get these two values as well. 16.16 and 19.83. Any questions about that? Why we did that? Why don't we add 12 again? Why don't we get the next ones? Why don't we get these two?
Over 24 hours?
Yeah, because it's beyond the scope of the question that it's asked. Okay. So here's our graphing calculator, and we verified those answers, which are right here. Example 4, solve 2 sine theta cos theta is equal to cos 2 theta for the interval between 0 and 2 pi. Selecting a strategy to solve. So this has double angle formulas. So this is a little bit of trig identities as well as actually solving for it. So the first thing I hope you guys notice that this value is equal to sine 2 theta. So the reason we did that is because we wanted to both work on both sides of the equation with 2 theta. Okay, that gives us the option to cancel out the 2 theta and to develop this formula, tan 2 theta is equal to 1. Okay, we do that by dividing both sides by cos 2 theta. So then we end up with tan 2 theta over 1 because the cos 2 thetas cancel. Any questions there? Alright, so now that I have that equation, I want to solve for 2 theta. So I take the tan inverse of 1, which is pi over 4. So the tangent ratio we know is positive in the first and third quadrant. And there's my related acute angle, pi over 4. So I'm looking for this angle now. So I'm going to take pi and add it to pi over 4. So I have 5 pi over 4. So my two angles are pi over 4 and 5 pi over 4. And remember, those two angles are not actually theta. They're all solved for 2 theta. Now you solve for the final angle. theta is equal to pi over 8. Theta is equal to 5 pi over 8. Could have actually solved for theta here. We could have said theta right away from this is pi over 8. And then just found the other one. So either way, they do it second. Finally, the last part is we need to add the period. This is the tangent function. Remember tan 2 theta. So our period in this case is pi over 2. So we take those values of pi over 8 and we add pi over 2. 5 pi over 8, we add pi over 2. And we keep doing so until we go beyond the range. The range is between 0 and 2 pi. So our last value would be 13 pi over 8. If we take the first value and we add pi over 2, we get the second one. That's why it says already determined. We take the second one, we add, we get 9 pi over 8. We take that value, we add, we get 13 pi over 8. And we don't keep going because we would be beyond 2 pi if we add it again. Okay? So these are our values. Any questions? All right. In summary, same strategies can be used to solve linear trigonometric equation when variables is measured in degrees or radians. Because of their periodic nature, trigonometric equations have an infinite number of solutions. When we use a trigonometric model, we usually want solutions with a specified interval.